Welcome to another episode of the Mapscaping podcast. My name is Daniel and this is a podcast for the geospatial community. So today on the podcast I'm talking with Vin Sharma. Vin is the VP of Engineering at FourSquare, and this episode is an extension of the previous episodes I've published in partnership with FourSquare. But today we're focusing on AI, and I know I say this a lot, we cover a lot of ground during this conversation. Let me try and help you understand what I mean with that. So we start off by talking about thinking machines. We move quickly on to a story about how snow in image backgrounds turns out to be a key identifier of wolves and dogs in images. We touch briefly on recognizing patterns, testing hypotheses, talk about the explainability of the outcomes of AI models. You'll get a brief introduction to something called vectors, and it's not the vectors that you're thinking about, all the way to the big question. That's right, we answered the big question right at the end of this episode. And of course, the big question is, when are we going to stop talking about AI? So we cover a lot of ground in this episode. I really hope you enjoy it. I will see you on the other side. Hi, Vin. Welcome to the podcast. You are the VP of Engineering at a company called FourSquare. So I guess a great place to start would be engineering what? What are you engineering at FourSquare, and how did you get there?
Hi, Daniel. It's really good to be here. It's been a long journey to this point at Foursquare. What we do at Foursquare is deliver location intelligence, and I'll explain this as I go along, to our customers who are businesses that want to make business critical decisions, things that matter, based on location data. And so what we do is build systems and techniques and methods that extract patterns and relationships from the movements of people across places in space and time and extract that pattern, represent it as a set of relationships, maps, if you will, that we can then deliver to our customers who then use that insight to make their decisions.
And have you always worked with spatial data? Is this something new to you, or is this, is this your bread and butter?
This is, in fact, new to me. I've been at Foursquare for about 7 months. Before that, I was at AWS, where I led a team that built systems for deep learning, which, again, we should dive into in a few minutes. And then before that, I was at Intel working on a project to build a cloud platform for car companies that were looking to invest in autonomous driving at the time, which is kind of how my AI interest became very focused. And before that, I was at Hewlett Packard for 15 years working on a variety of systems, primarily operating systems, Windows, Linux, and large scale servers and distributed computing systems, which is kind of what led me to big data. And then big data led to machine learning, and machine learning led to autonomous vehicles, and autonomous vehicles led to deep learning. And then that led to geospatial data. So it's an odd spiral of a trip, but it's true for most trips, isn't it?
Yeah, yeah. Wow, you have come a long way. So given that you can't see me making these air quotes here, but given, in air quotes, that you're relatively new to working with spatial data, how has that transition been? Is it difficult? Is there a lot to learn? We have this idea in the industry that the spatial is special. So I guess my long-winded question here is spatial special, or is it just another column in the database that you need to deal with?
It is, in fact, special. And one of the reasons I chose this role in this company is because Foursquare has access to this very special data and has had this ability to construct meaning from it for quite some time. And the reason it is special is because unlike most other types of data, and historically we've had a lot of corporate systems that store sales data, customer data. They've had obviously names and addresses in them, and you could argue that addresses are part of location data, and so they're within the broader context of geospatial. However, what has been very interesting of late is that we've seen the rise of tools like machine learning that extract patterns from data that is, whether it's records, rows and columns of tables, or tables with rows and columns of numbers and text, or more interestingly now images and videos and documents. But what's been less developed is the ability to extract these patterns and inferences, draw inferences from spatial data. and geospatial data has certain peculiarities that I've started to appreciate since joining Foursquare that make it both challenging and exceptionally interesting to analyze, and to bring machine learning to this realm of data is, I think, something that I'm going to enjoy, and I think a lot of our customers are deriving value from as we do that.
Hopefully, some of those challenging and interesting nuances will come out during this conversation. You've mentioned a few interesting words here, and let me just sort of rattle them off for you: ML, AI, deep learning, and patterns. But I want to start with this ML, AI, and deep learning. So I often use these interchangeably. Are they different? And if so, how? Perhaps it would be really helpful for myself and the listeners if you could put a few definitions around these. What are we talking about when we talk about ML, AI, and deep learning?
I should probably caveat this by saying I'm going to sound like a bit of a pedantic old fool, or or somewhat of a purist in this, but I've been interested in AI, artificial intelligence, since I was 10 years old, and that interest came from the original definition of thinking machines. In large part, came from the work that Turing and Claude Shannon and Norbert Wiener did back in the early days in the 50s and the 60s, that described systems that could think, as the heart of what an artificial intelligence program or charter would look like. What that means, if you really unpack it, is the idea that there are structures in the way human beings think. We reason. In order to reason, we first perceive the world around us, and we have multiple senses with which we do that. So we acquire data through these senses. We then construct some set of concepts based on that data. We then build a hierarchy of these concepts. We find structures and relationships among them. We then use various reasoning abilities, some of which we have to acquire very carefully and painstakingly through our education, to manipulate these concepts and the symbols and create new structures and new symbols from them. In other words, come up with new ideas. And then we express them through thought, as in, just the dreams or imagination, as well as just being able to think of new ways in which we can represent these concepts. And then we express them. We write them down, we communicate them, we talk, and we communicate through speech or other means. And most interestingly, we actually act again in the real world. So we demonstrate this intelligence through our behavior. So this broad scheme of human engagement with the world in a thoughtful way is what we think of as intelligence. And artificial intelligence, then, in that broad sense, means all of this. So it means perception, it means reasoning, it means knowledge representation, it means communication. Now, when you look at machine learning, it's a relatively small part of what I've just described as the full landscape of artificial intelligence. It is the part that, as it would suggest in the term, where you're updating your knowledge with new data. And so you're learning, you're adjusting your assumptions or your priors, if you're of the Bayesian bent, or if you're, simply acquiring knowledge, you're in some kind of a structure, whether it's a network of ideas or topics, then you're adding new topics or adding new relationships between existing topics. You're extending the memory of what you have acquired in the past with new elements that you've added to it. So this is machine learning, and you'll see many techniques for it. A lot of these techniques have evolved over the past 40 years, but there's one that has seen a resurgence of late, and that has to do with using techniques where the acquisition of this new data and the adjustment of prior knowledge is represented in the form of a neural network. So you have inputs of various data points that can be captured through, say, a layer of artificial neurons. And the neuron here is a very simplified version of what a real neuron cell in the human brain would be and look like and act. But it's a sufficient simplification. It's actually useful simplification. And what that does is that it then represents the data that it receives, encodes it in a very simple mathematical way, and then passes the signal to another layer of neurons. And if you keep adding these layers and layers of neurons and doing these mathematical operations, which are essentially like a weighted sum of all the inputs that that neuron has gets, and then kind of an activation function, if you will, a threshold that it has to that weighted sum has to meet before the next neuron activates, before it kind of sends a signal further back. So if you kind of layer these neurons upon neurons, you find that it can actually represent any kind of a signal, and it is a universal signal approximator in some sense. And what that gives you is a very powerful technique for representing knowledge in an implicit way. So you don't have to write rules to describe this learning behavior. You can just push lots of data at this neural network, and it is continuously adjusting its weights because it's comparing what it predicts against the real, reference, a label, if you will, where you've said that it should be a cat or a dog or a wolf, and the pictures that it's processing fall into one of those three classifications. And if they're correct, then it gets it right and it strengthens the weights. And if it gets it wrong, then it, adjusts the weights accordingly. And so over time, it seems to learn to recognize cats from dogs and so on. And so that's kind of what deep learning means, because there's lots of depth to these layers of neural networks.
Wow. If you were having any of those thoughts when you were 10 years old, you were a long way ahead of me when I was 10 years old.
No, when I was 10 years old, I really just wanted to build a robot that could be my playmate, and kind of had this bipedal, like an android. The data of Star Trek is really the kind of the notion. But the broader thought was that really, if a large part of the motivation is that there is a school of AI that came about because we wanted to better understand the way the human mind works. And the best way to do that is to actually try to build it. And when you try to build it, you struggle with the challenges of understanding the underlying structures and mechanisms. So, literally, the mechanism that constitutes the human mind is what the premise of the artificial intelligence project was, and it's at least one form of it was. And that was the most exciting part, and remains the most exciting part for a number of people in the field today.
If I had to try and recap this, I might be tempted to say something like machine learning is it sounds to me like it's a lot more focused on the acquisition of data, of the learning side, as opposed to the reasoning side. And for me, anyway, when I listened to what you said there, I started thinking about deep learning as the reasoning engine. Like it seemed to be in the name, a deeper process. And it sounded like a lot closer to the definition of AI as you gave it earlier on in the conversation.
I'm gonna caveat that. I think that yes, there is some recent work, particularly with the large language models, and you've almost everybody certainly heard of ChatGPT by now, where the newest version of it, ChatGPT 4, starts to show some amount of or has some indicia of reasoning abilities. But really, to be clear, the neural network is a statistical inference machine. All it's doing, in this case, the all seems reductive, but what it is doing is extracting patterns from raw data and inferring, in other words, creating a model that is too complicated to express in mathematical terms by a mathematician sitting at the problem and looking at it. So if you were to, for example, take a very simple problem of having points on a ruled paper, a sort of a classic, grid, and putting dots on it. And you now wanted to draw a line that goes through as many of these points as possible, a single straight line, and you expressed it mathematically as a formula y equals mx plus c, where m is the slope of the line and c is some kind of a constant that intersects the one of the axes. And so you could say, I'm going to adjust the m and the c until it seems to cover as many of the points as possible. Now, fundamentally, if you kind of scale this up, this is a regression problem where you're looking to reduce the regression to this line, as if you were to start to look at it not as a line, but as this complicated polynomial curve that represents all of these dots, and you're trying to fit the dots to the curve. Then that's really what the neural network is doing. in a sense. It's really trying to fit these data points into a curve. Now, in some cases, this could be many, many, many dimensions. So not just in like the X and Y axis, but maybe tens of thousands of dimensions in which these points are expressed. And so the neural network gets extremely complex and requires a lot of parameters. Now, it may appear to be reasoning in response to questions, but what it's really doing is really predicting the most likely correct response to your question, given all the data from which it has built this complicated multidimensional model that would be too hard for a mathematician to write down, but somewhere in the depths of the network architecture of the neural network is a combination of weights and calculations that leads it to the right prediction.
So you talked a lot about predicting the most likely outcome, and I want to head off in this direction and think about how we're going to use this to find patterns in just a second in geospatial data. But my understanding is that these models are amazing, but they're only as good as the data we put in them. And in a previous conversation, you gave this fantastic example about using a classifier to separate dogs from wolves. And I think it might be really helpful for the audience to hear this. Would you mind walking us through this example, please?
Of course. So one of the things that neural networks are famously good at, and it became particularly popular in recent times, was in sort of the classic detecting, cats on the internet, of which there are many. But if you kind of generalize from that problem, the idea is that you want to have images that have been taken by hundreds or maybe now billions of users that now are taking pictures on mobile phones, wandering the world. And as they do that, you want these images to be automatically labeled, tagged. You want images, you want the actual objects inside the images to be detected so that the human beings that took these pictures or are seeing them don't have to do this manually. So that's fundamentally an object detection problem. And you're looking for something that in the old days, the image processing algorithms would have to be handwritten, conceived of, and thought through, where you'd look for the edges, you'd look for the shapes, you'd like to match the shapes and the edges and start to construct these concepts. Now, all of that engineering that led into detecting these features that would allow a model to classify this input image as either a dog or a cat or a wolf have now been expressed internally within the neural network. And one of the cool things about this is that you now have to merely keep giving tens of thousands of examples until the neural network learns to recognize this, and it does this well. And so you could, and in a rather famous experiment, researchers fed it images of dogs and wolves because they're sufficiently close as species in the shape and form to where this becomes an interesting problem for a neural network. And it turns out after lots of training, the neural network did in fact recognize dogs and wolves correctly. But as you started to look at why, it turns out that the reason they were recognizing wolves as wolves is because more often than not, the images of wolves included snow in the background, whereas with dogs, they didn't. And so, what the feature that it is actually extracting from these training examples is not so much a particular attribute of the shape of the snout or the fur or the perceived gait in the image, but rather the background of whiteness of the snow that's a part of the image. And so the feature that's the most important for a neural network that it bases its prediction happens to be snow. And so what that is very suggestive of is a couple of things. First, that the what we assume the neural network does isn't necessarily what it does. And so there's kind of a hidden depth to it, very much in the hidden layers of the network, where the features that it is extracting in order to make these classifications may well be very different from what you've intended as a model trainer. Second, it takes discipline and it does require a particular stance of looking at model development from the perspective of responsible AI. In other words, the responsible use of a model in many ways requires that we treat these classifiers with a critical scrutiny, which means that we must look for what are the features on which it's making this classification, because Otherwise, these models are black boxes that may have predictive value, but their explanatory power or explanatory strength is also what we should be testing before we deploy them in production. So imagine if this were less, certainly classifying dogs and wolves is of academic interest and it's very useful. However, if this were a model that were making predictions on whether a candidate for a loan should be approved or not, and the loan application was based on a number of inputs. So when you enter in your loan application, you type in everything from your name, perhaps your address, and therefore your location. And implicit in that may well be the zip code, and with the zip code, the demographic, income, and racial composition of the neighborhoods in which you live. And if the neural network that makes a decision on whether or not to approve a loan application were to be inferring or making those decisions based on those features, that would certainly not be, first, legal, and second, it would deserve an explanation to the individuals on what basis their loan was approved or rejected. And so you want to be able to inspect the neural network or the machine learning model for the importance of the features on which it makes its decisions.
Whew, okay, we covered a lot of ground there. We have come a long way in a very short time. So I got a couple of things out of this. Firstly, the input data is important, and the next thing that I got out of it was this idea of explainability. I think we should save the conversation around how we explain these things later on, because as you pointed out, certainly it's important, for some scientific experiments or studies to be able to identify the difference between dogs and wolves. But it's a whole nother thing if we start classifying humans and disrupting their lives based on the outputs of these models, and that desire to be able to explain, like, why is this happening, why was this the result. I think this is going to be the background for an interesting conversation later on. We've been talking about this in terms of images, dogs and wolves and images, using a classifier to separate those two. And then we saw what happened, like, oh, it was classifying based on the background. Doesn't this become a very real problem also when we move over to the kinds of structured spatial data that Foursquare is collecting when we think about looking for patterns in this geospatial data?
Absolutely. And so there's a interesting parallel or perhaps even a metaphor of an image and a map. We could go down that path. But even without the obvious correspondence of images and maps, if you were to imagine that location data is like at its heart, the idea is that there's an individual, there's a person who either moved or stopped at or is stationary at a particular location on the planet, a latitude that can be represented by the latitude and longitude. Now, if you take those three components, and put them together, what you end up with is essentially an individual at a particular location, at rest, or in movement. And if you imagine that to be like a single pixel, and you start to put these pixels side by side, meaning you start to put the movements of individuals at a particular location, and you start to create a large image, much like a set of pixels would compose it. Now, have you seen those images where you have to kind of squint at it to make sense? And after you squint at it for 5 minutes, it looks like somewhere in the spiral you see a shape.
Yes, yes.
This is roughly what we are trying to do with the movement of people. In some ways, it's obvious. Obviously, there's a lot of people that have home addresses and have work addresses. They go from home to work, and between the times, that work times, you see a lot of movement that matches the pattern of people going to work and returning from work, going home. But there's also an enormous amount of movement of people that are going to other places besides home and work. They're, whether it's restaurants or movie theaters or events or stadiums and so on and so forth. There are billions and billions of places around the globe, and people move across them all the time. So it's those movements that if we were to look at them and start to see a pattern, this would inform so many things. And one of the most exciting things is that whether it's in the public spaces and the way that we build them and that we architect them, whether it's parks or roadways, or other public spaces, or in corporate decision making, whether it's to do with the way that shops and stores are located, or the supply chain or the web of supplies for goods and services are bought and sold and distributed. All of these decisions can be informed by a better understanding of these movements, of these patterns in the movements of people. And you shouldn't have to squint into the picture to be able to find this out. You should be able to have tools that really do this for you. And again, one of the most powerful tools we have at our disposal over the last 5 years is this amazing machine learning or deep learning capability that is designed to extract these patterns. And whether they're cats or dogs, you're really looking at these pixels in images and constructing semantic structures, meaningful objects out of them. And so we think one of the most powerful tools that we can bring to this problem of understanding the movement of people in space and time is to apply these tools to a different type of this very special geospatial data set or data sets and start to extract meaning from them.
So it's extremely important that you get it right. And again, I'm pushing this idea of explainability a little bit further down the road here. Is a totally different problem. So you're constantly like drawing on this relationship between pixels, in a certain region of a certain color and at a certain scale that they build up, they form a pattern. That pattern might turn out to be a face. That face has metrics and has landmarks, and we can capture those metrics and build up this semantic data about this region in the image. And of course, you're talking about the movements of people and saying, well, these build up to be a pattern as well. If we can capture the metrics of those patterns, we can start attaching semantic information to that as well. But we're talking about pixels, the difference between pixels, in my mind, unstructured data, data that does not have these semantics attached to it, and structured data that we already know a lot about. We've already labeled it, at least in my understanding. Are they two very different approaches when we think about starting to look for patterns, looking for these landmarks?
That's a really good question. So there's a couple of things you spoke about, and I want to separate these ideas because they're really powerful. There's one you mentioned labeling, and the other was structure. And so we want to separate these two because if you think of structure, traditionally the way people have described it is that the data has structure in terms of rows and columns, meaning it can be expressed in terms of there's an index that refers to its position in the table, and then there's a set of attributes or dimensions, in other words, fields associated with a particular record. And now you have lots and lots of records, so it looks like rows, and there's columns of fields or dimensions for each. And we have tools, databases, analytic tools that work with this kind of a structure very easily. And so we've been doing this for decades, and we do this well. What's different about geospatial data is that the index, the position of a record in that table, isn't just determined by its placement in the table, but actually in its by its placement in the real world. So it's almost as if what you need is not so much row 1 through row 300, but actually that there's some kind of a spatial relationship between row 1 and row 300. The place in row 1 and the place in row 300 have a particular spatial relationship because they're maybe just a mile apart. And you want to express that distance in a metric somehow. Or you might want to express the density of all the restaurants in a particular zip code as a metric somehow. And we should be able to extract these kinds of patterns from the records of places. So there's structure, but what you're looking for is a kind of meaning that is abstracted beyond the raw structure or the format in which the records are represented. You want the structure that's inherent in its geospatial, coordinates, and perhaps a grid that you use to represent the entire world or the globe, and then start to place these records on that grid. And now you start to look for cells that are close to each other, or the distances between those cells, and so on and so forth. One of the most powerful techniques in this space is to use hexagonal cells with which to grid the world and then use the relationships among the neighbors of these hexagons to start to look for these interesting patterns. And so we do that, right? Now, there's the other question about labeling. And that's somewhat distinct because what we're talking about is the difference between what you might hear as supervised and unsupervised learning. The notion here with labeling is that you know what is right and what is the desired classification or the desired outcome or output, and you're using that to correct the behavior of the system that you are training. So the machine learning model is essentially using the human labeled training data to adjust its weights and parameters so that it makes the right choice and produces the right answer for you. Now, there's a very different machine learning technique, and many of these are considered clustering, for example, where you don't give the label, you don't have a predetermined correct answer for the machine to calibrate against, but you're really extracting signal organically in some sense from the way that it is represented in the data. So it's like if there were a cluster of people that, were moving together at a particular location, perhaps there's an event. Maybe there's a rock concert at 5 p.m. on Friday in in a particular stadium, and that's what that event represents. And you're able to see that without having anybody told you that this is a rock concert, because it just so happens that the attributes can be inferred from the cluster of data points that you're seeing there with that spatial location, the time, and the nature of the people that are at that location. And so this is a different algorithmic approach. And I think that that too is hugely valuable. So we're bringing both types of approaches in very different ways, whether it's spatially gridding the system or inferring patterns from unlabeled data.
How important is geographic scale when you are running these algorithms?
I think it's critical to be able to look at it at multiple scales. So if we go back to the map metaphor for the way we see geospatial data, in much the same way as an image would represent ordinary objects in the real world, a map allows you to zoom in and zoom out, done well. Particularly with computer generated maps, you should be able to zoom in all the way from the perspective of an entire globe, the planetary scale, down to a very, very specific spot on the planet. And so to do that to maybe a 1 square meter region. And so you have the zoom in, zoom out ability, and you also have the ability to pan, so go left to right. And so we should take advantage of these conceptual tools to understand scale for geospatial data. So you can scale, in terms of the viewport, the size from left to right, or you can scale from top to bottom by zooming in to zooming out. And you can look at data at different granularities for each of these scales. So perhaps an event or a process, a geospatial process, right, that's happening at a very large scale or spatial scale, it looks very different at a microscopic, so to speak, scale. And so you should be able to kind of look for these emergent patterns at different scales. And I think that that's a really interesting analysis that we see when we bring these advanced analytic tools like machine learning and ML to bear on geospatial data.
There's two different approaches here, and please correct me if I'm wrong. But one is, okay, I have these tools, I have this incredible data set, and I'm looking for something specific. I am trying to prove a theory that I have. I've seen an example somewhere else, and I'm going into the data and actively looking for that. And I guess another approach would be I'm exploring. I don't know what I might find. I'm just looking for a pattern, and then once I find a pattern, I'll try and identify it and then zoom in or zoom out and see if it still exists there. When you are doing this kind of analysis, is there any one of these approaches that comes first?
If you approach this as if you would the scientific method writ large on geospatial data, you can look at the way that scientists pursue their research, both in terms of forming a hypothesis and then testing and validating the hypothesis. Now, forming the hypothesis, it's possible that we a clean slate, if you will, and you start by saying, I'm just going to look at the raw data and see what comes through and emerges from it. And so I'm just going to explore the data in the ways in which the tools allow me to do that. And this exploratory data analysis is a certainly a leading edge for the scientific method. And we could see this with geospatial data by, again, representing the data points on a map and just having the map express the underlying hypothesis to us, or one of many hypotheses to us, right? So you could say, oh, this looks interesting. Why is there such a dense concentration of restaurants in this particular neighborhood? And it turns out that maybe there's a demographic reason for the nature of these restaurants. Maybe there's a lot of working professional singles and are in a particular urban neighborhood that generates the kind of demand that would support a large diversity of restaurants. And so you kind of look for this hypothesis to emerge, and you can test and validate this by saying, well, does this hold true if I take the same demographic attributes and try to look for a different part of the country? Well, maybe I saw this in San Francisco, but is this also true in New York City, in Chicago, and LA? And you could find these dense pockets of urban enclaves which are sort of a hotbed of young urban professional, restaurant goers, right? So you could kind of create these clusters. You could look for these and test and validate them. My point is that there's certainly that as a viable approach, but more often than not, we're trying to solve a real world problem. If you are a city planner, you're trying to figure out what is the most effective location for a new park that I want in my city where it serves the broadest community of citizens. Or if you're a business and say you're a company that has a lot of store locations in Europe and is looking to expand into the United States, and you're starting fresh and you'd like to be able to place perhaps your corporation that operates a number of coffee shops. And so you'd like to find the best location for a coffee shop, and you'd like it to be within a certain distance from a competitor. You'd like it to be within a certain distance to a ancillary product or service. So obviously, it's perhaps you want a coffee shop right next to a bookstore or close to a bookstore. So these are all location decisions that you're looking to make, and you're solving a particular problem. And it's less about kind of a open-ended exploration of data as much as you have certain constraints. You're trying to solve a problem and you're looking to solve it as effectively and as quickly as possible, and you bring a different set of tools to that problem.
I would imagine that you know a lot more about your data and perhaps even in terms of its potential capabilities than clients, than people coming to you that have these kinds of problems. How do you balance this? Because if someone comes to you with a problem, that might be a very limited set of problems. They might want help with other things, but they don't even know it's possible. So my question is, how do you balance this? Do you just rush out to their market and say, oh, you've got a problem here, let's solve it? And or are you providing like, oh, we can also do this. We can also do this. Here are five other experimental use cases that we're working on that prove that this is also a viable product that you might like. Because it seems to me you need to help people understand what is possible in this world of machine learning and big geospatial data.
One of my past lives was working on operating systems, and it's been a guiding influence in the way that I've looked at a number of other subsequent opportunities. And this is one of them, where if you kind of imagine that if you were asking a company to enable a wide range of applications for the compute capabilities that it can deliver to them, right? So there's a broad general purpose technology called computing and storage, and you want to be able to serve as wide a number of people with that computing capability. And so, how do you do that? Do you start by creating individual applications that you then offer up and say, treat this as a role model, build many more of these, and you'll be fruitful and multiply? Or, or do we kind of look at it as an operating system and say, look, if I had a core operating system like Windows or Linux or Unix or something else, and I could also build a reference application. So imagine, when the iOS came out, it came out with a bunch of individual applications as well as the operating system. And so your iPhone, came with a Maps app and obviously the phone app itself, but there were a number of built-in apps that were provided by the manufacturer of the phone and the operating system. But what they were delivering was an operating system on which other people could build applications very quickly. And they made this really easy by providing a software development kit or tools that helped these application developers build these new apps very quickly. So if you imagine what we're doing at Foursquare is very similar. We do have this enormous amount of data. We do now have the tools with which to digest this data and extract patterns from it, make inferences, help drive predictions that we think are interesting. But we can only do so much out of our own imaginations. What we really need is the ability for customers to ask questions, to interrogate this data, and to build applications themselves that take advantage of these data points. And so if they want personalized recommendations of the places that they as individuals should visit because their friends have visited them too, or that the people who have the interests that they have in common have visited these places, or if they're businesses and they want to make these site selection decisions, they want to be able to build applications on top of our operating system for geospatial analytics. And so essentially what we're doing is taking a platform approach, and this is how we think of it, as building a platform that has the inherent ability to construct these graphs or relationships and express these patterns that are imminent in the data, but express them through APIs and then provide a software development kit that allows these programming interfaces to be useful to external application developers. Now, some of these applications we could build ourselves, but we certainly don't have any aspiration to build them all. We cannot. But we really would love to do is make sure that third-party developers can build location-based apps on mobile phones or location-based services as cloud services or a variety of other points of engagement with this data.
So if we focus now on the product services that Foursquare is going to build, and we come back to this idea of explainability, what does explainability look like today? So you gave this great example before of an algorithm that was actually doing a great job of recognizing or separating dogs and wolves. But when it came down to it, the thing that was making the difference was the snow in the background, was the background of the image, which doesn't seem like a very robust way of doing it, but it worked for a while. At least that's my guess. So build a product or service based on this huge amount of geospatial data you have and these deep learning models. And then the client says, hey, can you explain this result that I'm seeing? Can you explain why the model reacted in this way, why it chose this site?
And so the way to come at this is again, if you saw this as the model makes a decision based on the importance that it attaches to a particular feature among, perhaps hundreds of such features that it has extracted from the raw data, then there are techniques that allow us to essentially construct these features. So again, there's two ways. You can kind of see this as the neural network as a black box does make predictions, but you can, to some extent, do a series of what would essentially be ablation studies. You withhold a certain feature. So if you imagine in this original example that we talked about, I can remove the background from all the images that I feed the neural network and see the difference that the background makes to the classification, which is in fact exactly how this hypothesis that the snow in the background was causing the classification was tested and validated. So there are tools by which we can suppress certain features consciously to determine the difference, the perturbation of the model, if you will, by altering that input, right? So there's tests for this. But an interesting thing that we could do with geospatial data in particular is that even before we get to this advanced black box model that makes brilliant but unfathomable predictions from geospatial data, we can construct these features that are easy to understand, that have transparency to them. And so then the recommendations or the predictions that our customers build can be built with their complete knowledge. So, in other words, a data scientist or an application developer could say, I now have a set of features that represent home for a group of individuals or work for a group of individuals, and these are different features. I can express layers of interest. So for example, there's maybe a cohort of 25 to 35-year olds who like fast food, and so this is a feature vector that I can then use in predicting something that is of value to me in the application that I'm building. So what I'm trying to say is that we as Foursquare are starting to look at it in two different ways. One is where we certainly have the models that do these predictions and recommendations for you and personalize them. And the proof is in the pudding. Did it work for you? Did it have the predictive value that you expected? And did you get the satisfaction of discovering a place that you actually did in fact like as it was predicted for you? And we get the feedback and we retrain the model until we get it, really perfectly tuned to the individual's behavior. But the other approach for businesses is to say, well, we've got this raw data, but the raw data has edges, has shapes, has structure, and we can then express those structures. And you can do with those structures, edges, shapes, and so on, what you would like to do. So you can decide whether you want to, use that to predict a wolf or versus a dog, but you could also just use that essentially as a feature vector to drive your own applications in a very transparent way. I don't know if that helped. The feature vector is a kind of a term of art where you think of it as a series of fields representing a particular feature, and whether it could be the age, the gender, the last 10 locations that a person visited, but no identity, right? So we would basically mask the identity of the individual, so they're not necessarily tagged to a particular name and person, but you have a sense that this represents an individual movement.
So yeah, I'm going to be perfectly honest here. I'm not sure I totally understand. I am not the data scientist that you are, but I gotta say, it sounds fascinating, and it sounds like a really interesting way of detaching the person, the individual from this, and then we're looking at these series of features that you're talking about, this vector, and look for other vectors like that, and based on those other vectors, we can, if we find similar characteristics out there in the world, we can start to infer perhaps these characteristics, perhaps, and make predictions based on that.
That's exactly right. That's exactly right. So you could look at these distances between these features or the density of these features in a particular spatial location or over time. And so you can start to make these inferences without revealing or identifying the individuals involved. And so then there's a host of applications where they're not advertising. Look, there's certainly a lot of location-based advertising in the world today, and that is a large part of what location data is used for, is to build personalized advertising because, well, I mean, advertisers, for as long as you can turn over a box and it can become a soapbox for you, there will be advertising in the world. The choice is, do you want the advertising to be personalized to your interests, or do you want it to be just generic, what everybody, a broadcast message that may not be relevant to you? So there's kind of a bit of a trade-off, particularly where the services that a business provides to their customers are supported by the revenue from these advertisements, right? So, given that, there's advertising businesses built on location data where it's important to be able to identify the individual. But there's a whole host of applications and use cases and potential for geospatial data that doesn't have to do with identifying the individual, but looking at the movements of aggregates of individuals, groups, cohorts, communities, and neighborhoods, and the patterns of movement at city scale. And these are all fascinating new approaches to doing more with location data that we at Foursquare are excited to empower.
It's funny that advertising is the scapegoat. The advertisers are always the bad guys, right? But I think we're just poorly targeted advertising. That's what people are pushing back against. So I'm really into. I have a compound bow, so I do archery. I stand outside and shoot my bow. I have a gravel bike that I love to ride. Please advertise to me all day long about archery and gravel bikes. This is, I don't see it as advertising. This is stuff that I'm interested in, so please send it to me.
Yes.
And I'm not just saying this, I'm actually like it. This is actually the way I am. I think a lot of other people will relate. They might have car magazines at home, or home design magazines, or whatever. What is that other than advertising? The point is, it's really well targeted advertising, and we don't like these are messages we want to get. So yeah, I don't want the Nike shoes to follow me around the internet all the time. I'm not into that kind of advertising, but correctly targeted, yeah, I mean, all day long. Yeah, I love it. I want to move off now. So I feel like we've talked about AI in some depth at the start of this conversation, what it is, what it isn't. We've talked about this idea of recognizing patterns and the difference between structured and unstructured data. We talked a little bit about labels, what it means to have a label. And then we talked about these different ways of mining through this data, looking for patterns at different scales, and then how we test our hypothesis by perhaps removing some parameters and putting them back in and seeing which ones have have a real effect on it. And then you describe this idea of these vectors, these attributes, fields that when linked together, we can look at the density of them, the distance between them, and say, okay, when we see this in the database, not when we see a person, but when we see this, we can infer these predictions with some level of accuracy. And I really appreciate that. I've enjoyed the conversation. It's been at times a little bit over my head, but I've enjoyed it nonetheless. If we step back a little bit now and think about AI, way more broadly, I can see a lot of benefits and I can see a lot of downside to this stuff. And every time when I hear people talk about AI, there's this underlying idea of it's becoming easier, it's becoming democratized. Would you agree with that idea that AI is becoming democratized?
AI, it covers a lot of ground. It speaks to a lot. The field of AI has certainly been democratized in that when I was in that field as a graduate student in the early 90s, there were, maybe 2,000 PhDs in neural networks published in any given year. Now there's, I think, 200,000 in any given year.
Wow.
And so that just means that a lot more people are obviously interested in this field, and there's different ways in which they can engage with it. They can experiment with it with the tools that are now available in open source, with the data that's now available in large part, through the ability to look at human behavior online and scrape the web, so to speak, right? So that in and of itself means that the ingredients with which AI capabilities are built are now widely available. The tools are widely available. The knowledge is widely shared. And certainly, yes, that's democratized. Now, there's a tension here because for you to be able to build truly advanced, powerful, cutting edge, leading edge AI, there's AI capabilities. You have to have sort of a concentration of data, the concentration of compute capabilities to process that data at the scale that you need for these neural networks, and the responsibility, sort of the sense of responsibility to test and validate this before making it widely available for users that may or may not understand the limitations and the implications of these models. So I think that there's still a fairly concentrated ability to amass the data, amass the compute power, and to treat it responsibly. In other words, there are a few obviously well equipped organizations, institutions, both private and public, that are able to do this. But if you wanted to build the equivalent of a chat GPT today, then there are some recent developments and hold that aside, but it would have been really, really hard for an individual to build the equivalent of a chat GPT model without sort of this history of institutional support, the ability to access cloud computing resources, large amounts of data, and process it and bring the skills that you need to advance the field. So maybe I would temper that. Now, what it does promise, though, over the next 10 years is that we will see, because of this, incredible explosion in interest and the ease with which these models and now tools can be applied to various domains, that there will be a self perpetuating or perhaps a positive feedback loop, put it simply, in the way that new industries and companies and businesses and organizations will use these models to personalize their services for their end customers, to optimize their supply chains or their internal processes and generate more revenue, be more profitable. All of this means that there'll be more investment in AI, which then drives this growth. Now, it's not a perpetual motion machine. There will be limits to growth, but what it does promise is that over the next 5, 10 years, we should see an acceleration of these core capabilities to a broader range of industries. So I do think that you will see this democratization of which you spoke.
You answered that like a true data scientist, and I'm just going to leave that out in the air, and you can, you can decide if you think that was a positive thing or not. It was, but when I was listening to you say that, answer that question, this man is a data scientist. He has to be. So I want to round off this conversation, which I have
Sure.
really enjoyed. I hope you
I'm
understand
glad.
that. I
I'm
really
relieved
enjoy.
to hear that.
I have really enjoyed talking with you. It's eye-opening. It's intimidating talking to someone like you, to be perfectly honest. But at the same time, I feel like this is incredibly important. The more conversations I have like this, the better it is for me. The more conversations I think we make available to the community, the better it is for the community. This stuff is here, it's happening, and we can't just stick our heads in the sand and pretend like it's not. I think it's really important to understand it. If we understand it, perhaps we can use it, perhaps we can point it in directions that we think will be helpful for all of us. That said, when do you think we're going to stop talking about AI? So here is some context. So I studied geography at university, and part of that was GIS, remote sensing, Earth observation, spatial analysis. Even back then, so 10, 12 years ago, at no point did I say, I'm doing computer spatial analysis. Yeah, I'm doing spatial analysis, and of course, I am using a computer. When do you think we'll stop saying we're doing this in AI and instead just say We're doing this, and of course we're using AI. How else would we do it?"
Yeah, that's a really good question. One of the historical, I guess, trope within the field of AI is that when a technique is developed in the context of AI, where the field of AI has produced this technique, research in this field has produced a technique, and it starts to be used in mainstream and it becomes very popular, it's no longer considered AI because it's now just broadly computing. And so we see this play out over and over again, whether it's object-oriented programming or PageRank as an algorithm that's used in search to identify, to find results that are particularly relevant. So there's all of these methods and techniques that AI has spawned that once they get to a certain level of broad acceptance, I think they're not no, just chess playing, for example, playing against a computer on a game that when it was first thought of as a meaningful test, chess was the game to beat. But then afterwards, it's now has been Go, and until the machine beat the best Go player in the world. And so you start this you see this kind of a continuous moving of the goalpost. I think that there's for better and for worse, we live in a world where branding fields is important because that produces sources of funding because the field has a cachet, has power to attract funding for whether it's venture capital or institutional funding from governments, which means that there's kind of a prestige associated with the field, and AI currently has an enormous, immense amount of prestige, and so that's going to be hard for people to give up. And so I don't think that it's the term is going to disappear anytime soon. Particularly now, it's almost at I don't know if it's at its peak, but it's certainly rising. It's ascendant. But the techniques in the field won't be considered, perhaps won't be seen with the same kind of the glow in the same glow as they are today. If that answers the question.
Yeah, it certainly does. And I think that's really insightful, that idea that AI, well, it's a brand and it's a marketing strategy. I guess it also offers an explanation. Like, do you have 1,000 people sitting somewhere in the Philippines, and just as an example, working on finding all the trampolines in Denmark on satellite imagery? How are you doing this so quickly? I think AI offers an explanation for this. Oh, we're automating it. It also offers that explanation that and yes, this is repeatable. This is not a one-time thing. It feels like because a computer's doing it, yes, we can do it again next week if you also need it then.
Yes.
And that branding idea, we're not doing the same thing we've always done. If you want to invest in something, invest in us because we are using AI. We are using the tool of the future. I mean, I can totally see it from that perspective.
Yes, and so I do expect it to persist and continue and to grow. But I do think that some of the things that we're talking about today as conversational agents and, or image synthesis and or generating deep fakes, for example. These are techniques in a particular with a certain cache at a point in time, and those will change and evolve, and we'll move on to a more interesting problem for the time and the age in which we live.
I was thinking about this the other day, and I'll be interested to hear your take on this. And my thought was, it's interesting that in the scientific world, if we make a model of something, if we might say we are, instead of saying we're faking this, we might say we are simulating it, trying to replicate it. And that seems like a perfectly logical approach to figuring something out, to trying to understand it, to seeing what'll happen, to creating this place where we can run experiments. But then we have this idea of deep fakes, fake news, and there it's not a positive thing at all. There it is something very different. But the heart of the idea is quite similar, at least in my mind. Again, I'd be curious to hear what you think. But this idea of I'm going to create a simulation, I'm going to create something that looks like the real thing and use it to test a hypothesis.
I think it's absolutely brilliant. It's something that we're very excited about. If you look at urban studies at scale, being able to, no matter how high the fidelity is of our data collection, we are unlikely to have all of the data that we need for all of the time that we need in order to come to a decision. But, much like we talked about those dots on the ruled paper, there are techniques that allow us to interpolate the dots and extrapolate from what we have till you get to what looks like a pattern. And that pattern is insightful. And yes, there are caveats that say, well, this is provisional, assuming all of this. But I think it's still instructive and informative, and it advances the field, and it supports and accelerates the decisions that you need to make. And so I do think that there's a huge value in being able to do simulation studies with location data, particularly of movement of people and the data we have. And there's also, it supports a privacy preserving method by which to do this, right? Because you're really working with synthetic individuals in some sense, and there's no privacy loss or risk to the privacy of real individuals when you start to do that. You still need a basis, a foundation, a germ seed, if you will, with which to construct the simulation, but it supports a better application. The heart of your question, though, is that of intent. And so, yes, whether it is AI, machine learning, deep learning, location analytics, or synthetic, simulated environments, there's potential for misuse and misapplication, for irresponsible use, right, without either the consent of the individuals involved or the expression or declaration of limitations. And that there's nothing, there are ways in which the technology can support it, and there are ways in which it masks over it, but we as informed citizens have to remain vigilant as we look at these technologies as they're evolving. And so I don't think that that's solved by new technology. It's just compounded, and it's kind of, the same problem persists. It's not that the technology is value neutral, to be clear. It's that the values with which we shape the technology emanate from the society in which we live. And so we are responsible for shaping the technology that we use, and that never changes.
And I think this is probably a really good point to sort of round off the conversation and to say thank you. Thank you very, very, very much. And I mean it. Like you have done a fantastic job of walking me through a lot of these complicated subjects. And I really appreciate it. I feel like I've learned more. That said, I am definitely going to listen to this conversation several more times and probably take some notes, which will lead to some further sort of research. But anyway, thank you very much. I've really enjoyed talking with you. I appreciate your time.
Thank you, Daniel.
If somebody is listening to this and they think, how can I reach out to this person? How can I learn more? How can I continue this conversation? Is there somewhere they can go to do that?
Absolutely. I'm easily approachable on Twitter. My handle is CIPHR, Cipher, or you could shoot me an email at vin@foursquare.com.
Thanks again for your time. This has been an absolute pleasure talking with you.
Thank you, Daniel. The pleasure is entirely mine. I really had a wonderful time.
I hope you enjoyed that episode with Vin, and I hope that we can agree that we did actually cover a lot of ground in there. This is part of a mini-series that I have created in partnership with FourSquare. So some of the other topics we've covered in the past that you might find interesting. There's an episode called All the Places of the World. So this is about FourSquare's data, how they collect it, how they process it, how they derive meaning from it. Designing for location, how do they protect people's location privacy? Spatial knowledge graphs. So I thought this was really interesting. This is a move away from spatial joins and perhaps a traditional relational database that you know to a knowledge graph. There's also an episode called Big Data in the Browser. So I thought this was really, really interesting. And it made me understand or made me realize how complex it actually is to do analytics in a browser. Anyway, those links and more will be in the show notes of the episode that you're listening to right now. If you're interested, they're there. Otherwise, I will see you again next week. I hope that you'll take the time to join me then. Cheers.